This worksheet is going to be an introduction to stereoisomers. The first problem, we're going to be looking for stereocenters in these molecules. And I want to just kind of begin by saying that stereocenter is also referred to as a chirality center. It's also referred to as a chiral carbon. Maybe some other things too that I can't think of off the top of my head. So there's a lot of different terms that we use interchangeably in place of stereocenter. I know myself, I say chiral carbon pretty frequently. So we're looking for the stereocenters or the chiral carbons in each one of these molecules. In order to be a stereocenter, the carbon atom has to have 4 bonds, which just is going to immediately rule out anything with double bonds or triple bonds. And these 4 bonds need to be to 4 different things. They don't necessarily need to be to 4 different atoms. We're looking at, the whole entire package, everything that comes off of a carbon. And I'm actually not going to start with the first molecule on the list because cyclics are a little bit trickier to deal with than straight chain molecules. So we're going to go in this order and then we're going to come back to this one. So a lot of times with these, the first thing that I like to do is just identify all of the carbon atoms in the molecule. So I'm just going to begin by highlighting all of the carbons. We'll do it in like this bright pink color. And then what I want to do is just start eliminating carbon atoms that I know cannot be chiral. For example, a carbon atom with a double bond cannot be chiral because it only has 1, 2, 3 bonds. And any methyls, any methyl group, so a CH3, methyl groups also cannot be chiral because they have 3 hydrogens attached, so they don't have 4 different things. And then we also have, in this one, we have a CH2 group. That cannot be chiral because it has 2 hydrogens, 2 identical things. So this molecule has only 1 chiral carbon or 1 stereocenter. There isn't a conventional way that we notate a stereocenter. So like when a problem asks you to find the stereocenters or mark the stereocenters, there isn't a chemist way of doing that. You can, like what I've done here, just dotted it, or sometimes people point arrows at them, or sometimes people put asterisks by them, whatever. So here, let's do our next one. Let's start by finding all of the carbon atoms, and then we want to eliminate CH3 groups because they have 3 identical things. We also want to eliminate CH2 groups. We're down to just this guy right here. So we want to ask ourselves how many different things are attached to this carbon. It has a hydrogen, it has a bromine, it has an ethyl group, it has an ethyl group. Because it has 2 identical ethyl groups, there are no chiral carbons, no stereocenters in this molecule. Let's take a look at our next example. There's all of our carbon atoms. Let's eliminate our methyl groups because we know they can't be stereocenters. This carbon atom has a hydrogen, a methyl, an OH group, and whatever we want to refer to that whole big piece of the molecule. So this one has 4 different things. This carbon atom has an OH group, it has a methyl group, it has this portion of the molecule, which is different from this portion of the molecule. So this one is also a stereocenter for unique things. This guy has a hydrogen, a chlorine, a methyl, and all of this mess. So it also is a stereocenter. 3 stereocenters in that molecule. Here's our next example. We've got all of these guys. We want to begin by eliminating the carbons that are part of that double bond. Carbons that are part of double bonds or triple bonds cannot be stereocenters because you have to have 4 total bonds. Let's get rid of the methyl groups. Let's get rid of the CH2s. This guy has 0 stereocenters or chiral carbons. So now we're back to this one right here. So let's just kind of start by taking the same approach. Let's identify all of our carbon atoms. We don't have any double or triple bonds here, but let's eliminate all of our methyls. And let's eliminate all of our CH2s. So we've got all these CH2s out here. That leaves us with this guy and this guy. So what about these? So this carbon atom right here has a methyl group, it has a hydrogen, and then it has the ring attached. And this is kind of a confusing situation for students because they can see here's one thing, here's a second thing, and then isn't this just a third thing? So maybe doesn't this guy only actually have, well, we know it has 4 bonds, so it's not having 3 bonds, but is it only bonded to 3 things, even though it has 4 bonds? So that's why these cyclics are pretty confusing. When we're looking at the carbon atom that is a part of a ring, a carbon atom that is part of a ring, even though it is bonded to, if we want to think about it like that, it's really only bonded to 3 unique things, it does have 4 unique bonds. And so for the 2 bonds that are inside the ring, we want to kind of treat them as 2 separate collections of atoms. And the way that we do that is by looking at the bond to the left in this case, and comparing it to the bond in the right, thinking about the sequence of atoms that are connected as we go that way around the ring. So if we start here and we go this way around the ring, we have a CH2, 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 and then we come to this, branched methyl group. Now we want to compare that to the other bond in the ring. So the first bond in the ring we decided was a CH2, 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 and then we run into this methyl group. If we look at the other bond in the ring, we run immediately into the methyl group, and then we have CH2, CH2, blah, blah, blah. So for this particular carbon, as we go to the left around the ring and as we go to the right around the ring, we see that we have different connectivity or different arrangements of atoms as we move around the ring. And for that reason, we treat this bond different from this bond because it has a different connectivity and a different arrangement of atoms. So this atom, this carbon, back to this carbon, it has 4 unique things. It has a methyl group, it has a hydrogen, it has the counterclockwise path around the ring, which is different from the clockwise path around the ring. So that makes this a chiral carbon. And for this guy over here, we'll practice that again. Even though it's identical, we'll just kind of walk through the thought process. We have a bond to a methyl group, we have a bond to a hydrogen, and then we have 2 bonds inside this ring, and our job is to decide if these 2 bonds in the ring are the same or are they different from each other. So we want to think about, what if I move in the upward direction here? I'm going to run immediately into the methyl group. What if I move in the downward direction? If I move in the downward direction, it's going to take me quite a while to run into the methyl group. Because of that, the path this way versus this way are unique. They are not identical to each other. They are different from each other, which makes both of these stereocenters. This can be pretty tricky, so this is something that you want to practice quite a bit. The next question is asking us to draw the enantiomers of the following compounds. The enantiomer is the mirror image. There are a lot of different ways that we can, or a lot of different strategies that we can take when we're being asked to draw the enantiomer. To be clear, there is only one enantiomer for each molecule. Every molecule only has one enantiomer, but there are multiple different ways that we can represent that one enantiomer, or multiple strategies. And I'm going to do my best to show you all of those different strategies. I'm going to start with this molecule right here, just because it's kind of at the bottom of the page and easy to work with. So one method that we have when we're asked to draw an enantiomer is to imagine a mirror. So we could say maybe there's a mirror on the side of the molecule, or maybe there's a mirror at the bottom of the molecule right here. And then our job is to just simply draw the mirror image of that molecule. And we can literally put that mirror wherever we want. Gotta be careful I don't screw it up, because drawing, looks like there we go. Drawing the mirror image is not my preferred method, so I have to think about it a bit. So this would be one way. This is a representation of the enantiomer of this molecule. There are other ways that we could represent the enantiomer, but this is one accurate way. And you can put that mirror anywhere you want. So you could put it on the bottom, or you could put it to the left, or you could put it to the right. Here I'm going to do that same strategy again, but this time I'm putting my mirror off to the side. So there's another way of doing it, like that. An easier way, my preferred way of doing this is still the mirror method, but we imagine in this case that the mirror is on top of the molecule or underneath the molecule, which is really hard to it's kind of hard to visualize, and it's definitely hard to draw. When we use this strategy, what we do is we redraw the molecule, but all that we need to do is convert all of the wedges into dashes and all of the dashes into wedges. Now, it's really important that you recognize that these are two different ways, two different approaches for drawing the enantiomer, and you can't mix and match them. So either you straight up draw the mirror, and drawing the mirror means that you don't change wedges and dashes. Wedges stay wedges and dashes stay dashes, and you're just changing the, like the orientation of the molecule. If you are using this strategy, everything stays in exactly the same spot, but you change your wedges to dashes and you change your dashes to wedges. It's pretty common for students to try to like mix up those two different strategies. So they will, like, let's say, pretty common error is that somebody will use this method, but they will also change the wedges into dashes and change the dashes into wedges. And if you do that, it's just straight up wrong. It's actually just redrawing the original molecule. It's not changing it at all. Now, the last problem on this worksheet is referencing a problem out of the textbook. It's got a whole bunch of pairs of molecules, and we're going to do a kind of a different version of the problem than what the textbook asks. We're just going to determine if these molecules are enantiomers of each other, which would mean that they are mirror images, or if they are not enantiomers. So this would be anything else. And that's not exactly what the textbook is asking us to do, but that's what we're going to do. So I'm just going to, what I'm going to do is I'm going to use the letter E for enantiomer, and then I'm going to use NE for non-enantiomer. And I'm going to kind of skip around in this, like finding the ones that sort of appeal to me. I see this right here. That's like the first thing that I notice. This is two molecules that are drawn using that strategy that I just showed you, like leaving everything in the same spot, but changing the wedge to the dash and the dash to the wedge. So just based off of that, we would classify these guys as enantiomers. Now, those of you that might be kind of a little bit advanced, you might be saying, wait a minute, they actually aren't enantiomers. They are actually just identical molecules. And that is accurate, but based off of this is just sort of a very beginning introduction to stereochemistry. It's totally okay if somebody looks at these and sees them as enantiomers because we haven't really gotten to advanced topics yet. Here is one that is sort of like a mix match of both of those strategies that I showed you. So this is one that's drawn with a mirror right here, but in this case, they also, not only did they mirror it, they swapped the wedge for the dash and the dash for the wedge. When you do that, you are redrawing the molecule identically, which means that these two are identical molecules. So these are not enantiomers of each other. Here's one right here where the molecule has been drawn with the wedges being swapped for dashes and vice versa. So we're going to call those enantiomers. And again, if you are advanced, you're going to say, no, they're actually identical, which is true. But again, we're just focusing on pretty basic topics right now. I'm like, my eyes are kind of drawn to this one up here, like what's going on? Because one of these has a wedge, but the other one doesn't. And if you look at it closely, you'll see that these are actually constitutional isomers. This one has the bromine on carbon number 2. This one has the bromine on carbon number 3. So that is not an enantiomeric relationship. Those are going to be not enantiomers. And what do we got over here? Let's take a look at this one. This is like a double bond situation. These are not mirror images of each other. This is a different type. This is a type of stereoisomeric relationship, but not enantiomers. They are not mirror images of each other. This one looks like we are using the strategy of changing the wedge into a dash, changing the dash into a wedge. So we're going to call those enantiomers. And this one looks a little tricky. Like, we always have to be a little bit tricky when somebody has changed the direction of the carbon skeleton, like has been done in this case. So this is carbon number 1, carbon number 2, carbon number 3 has the methyl on a wedge for both of them. Carbon number 4, carbon number 5, carbon number 6. So those two are identical molecules, not enantiomers. And I've saved this one for last because this one looks a little bit tricky. Again, because it's been redrawn in a different orientation. Like my mind wants to kind of put benchmarks to draw things in the same spot. I don't like it when things get sort of twisted around. There's enough stuff to sort of be imagining in our heads. So what I'm going to do is redraw the molecule that's on the left, and I'm also going to redraw the molecule on the right, but I'm going to orient it in the same direction so that carbon-oxygen double bond is going to be pointing in the same direction. So I've moved this guy down to here. Opposite the carbon-oxygen double bond is a wedge, or excuse me, a dashed methyl. And then if I move it this way, I move this bond over here. I've moved this bond up here. That means I'm moving this bond over to this spot. So I've got a wedge going in this direction right here. That's tricky. That's tricky. It's not exactly like what I'm looking for. Like at first I might think, whoa, there's no relationship there, like not an enantiomer, everything is connected, kind of funny. But I want to remember that I can flip this guy over like a pancake. So I could just take this whole entire molecule and flip it. If I flip that whole molecule like a pancake, that methyl group over here is now going to end up on this side. This methyl group is going to stay on the same spot. If this methyl group was, what was it? It was a wedge. When I flip this guy like a pancake and it moves the methyl group to the other side, it's going to move it over as a dash. Also, when I flip it like a pancake, that methyl group in the back that's pointing down is now going to be pointing up, because remember, I've just flipped it over onto its back. And when I draw it like that, I can see that these molecules are identical, not enantiomers.